Welcome to the sixth and last course. So we start without waiting for stragglers with some recapitulations, so you'll have an advantage over them. Well, given the topic, I could even talk in French, but yeah, probably that's a bad idea since we started in English.
But you have people in the virtual.
No, let's talk in English. So, last time I introduced the statistical models called loop models, and now we will want to compare them to the conformal field theory. So, what are the main features of these models? So you have, well, parameters starting with n, or the loop weight. Well, in fact, it's the weight of contractible loops. Okay, and then we started to introduce some vertices. So we have here vertices that change the weights of loops. So a loop, well, let me do the diagram here. A loop around this vertex has an arbitrary weight, W, some complex number. So, well, I call them vertices or punctures maybe. So let's say this is a weight-changing puncture. And then we had other types of punctures where a number of open loops can end. So the number of open loops is called 2r. It's an integer. So we have this parameter r. And then we had an extra parameter s, which was a kind of angular momentum. So that was, let's say, loop ending puncture. And it came in the statistical sum. It comes with a factor, a weight factor, which depends on the loop configuration. So we could call it WRS, and which is essentially e to the is over 2 sum of theta. So theta are the angles of all these loops with respect to some reference direction. And then from these ingredients, well, we can build correlation functions. We can build, by combining these vertices, we build combinatorial maps, and to each combinatorial map, we associate some sum, statistical sum, which we'll consider as a correlation function. So, how do I identify this with conformal field theory? So the basic assumption is that the punctures are primary fields. So I wouldn't really know how to justify this assumption. But okay, let's assume that they correspond to primary fields. So to make the identification, well, historically, people have done some constructions using free bosons, which are not always completely convincing. So I try to give a simple argument without introducing extra constructions. So let's see if you find it convincing. And instead of starting with the beginning, which is the basic parameter n, I want to start with the end, with this loop ending puncture. And that's because they have discrete parameters, so it's easier to identify discrete parameters than continuous parameters. Yes?
A small question about how do you define the weight? I think we've already discussed last time, but so I expect that the theory is dilation invariant, or yes, you can make some kind of rescalings. And when you define these angles theta, as I remember, you take them to be the angles on a given diameter, right? You define a certain diameter around the puncture.
Right. So I draw such a circle and measure the angles on this circle.
Yeah. But then it's not invariant by rescalings or things like this.
Right. So the conjecture is that the result should not depend on the side of this circle. So R is the side of this circle. If you measure it in lattice spacings, for example, the assumption is that R is much larger than 1, so you have a lot of sides inside this circle, and it's also much smaller than the size of the whole lattice. And, okay, so what should not depend on this choice is not the angles for some particular configurations. Of course, this depends on the choice. What should not depend on it is the whole statistical sum over all configurations in the critical limit. But that's a conjecture, admittedly. Other questions?
Can you remind? I mean, I'm sorry, I was not here last time. So could you just define this?
Yeah. So that was the reminder. I just did that. So we start with contractible loops, so they have some weight n. Then we add punctures, which can change the weights of loops around them, so arbitrary weight W. And these ones, these punctures, I call them loop-ending punctures, but they can be called water-model operators if you want. So a number of punctures n there, 2r is this number. And in addition, they come with a weight. I mean, in the statistical sum, for each puncture of this type, you have a weight with an angular momentum s. Such the weight is exponential of is over 2 sum of theta. So thetas are the angles of these loops compared to reference direction.
Notice that they are watermelon exponents. So where are the loops?
The loops, I mean, this is an open loop, if you want, which ends at this
Just
point.
length. You don't need loops.
Yeah,
Number.
I'm calling them loops just because I want to say the partition function is the sum over loops.
Still not necessarily loops. Okay, so this is different from the usual exponents you have for these vertical lines.
Well, at the moment we don't yet know the conformal dimension of the corresponding fields in the CFT, so that's what I'm going to the earth now.
But this weight is the standard weight, WRS.
No, WRS is not the well, it's just the weight in the statistical sum. So you have this Z, which depends on some combinatorial map, in fact. So let's say it depends on M, a map, which means how you connect all these vertices together. For example, that's a combinatorial map. And, well, it depends on all the parameters. So it depends on N, on the Wi, so the W's of the various punctures, and also on the parameters Ri, Si of these other types of punctures. And that was the sum over all loop configurations, so non-intersecting loops, including these open loops, of all the products of all the weights. So you have n to the number of contractible loops. You have for all the non-contractible closed loops, you have this weight Wm, and you have also for each weight for each puncture of this type, you have also this weight factor WRS, which depends on the particular configuration. So, and then the claim is that this will correspond to some correlation function in the CFT, but now we want to know which correlation function. Okay.
So you have only in number of lines and in ULs.
No, and the number of lines, yeah, but R is not integer.
Oh.
R is not integer. So we have in the CFT, we had fields, non-diagonal fields, which were called VRs. If you assume that there is a degenerate field 1, then R has to be integer, And S, well, have to make sure that the conformal spin R times S is integer. So, no, I'm assuming it exists, but in the sense in the extended spectrum. Okay, so these parameters look a lot like these parameters, of course, which, but this is just a choice of convention. So how can I argue that they are in fact the same parameters? So the first thing is that R not only takes the same values, but it has obeys the same constraints. So the constraint is that R is conserved modulo integers. So in the loop model side, this is just because you have to contract all these open loops. And in the CFT side, well, this was again due to the existence of distributional field and an argument about monodromism of fields and single validness of correlation functions. So this matches. Now I would like to argue why the S here is the same as the S there, but that's not so difficult because R times S is the conformal spin. So it is a really geometrical quantity, and that on both sides I can define and compute this quantity. So in particular here, this conformal spin tells me how a correlation function should behave when I make some local rotation around this point. And what happens if I make a rotation by delta theta? Well, all these angles term delta theta, and I get an extra factor from this WRS. So WRS picks a factor e to the IS over 2 sum, a sum with 2 R terms of delta theta, right? Which eventually is e to the I R delta theta. But this is exactly how primary field of conformal spin R times S behaves under rotation. If you remember how primary fields behave under well, global conformal transformations. And therefore, R times S is the conformal spin both in the loop model and in the CFT, so I can identify these parameters. So the conclusion is that VRS is really, and this primary field is really a loop ending puncture. Okay, from this, in fact, I'd like to deduce the parameter W, the weight W of a weight changing puncture. And I can do that because in the CFT, weight changing puncture is a special case of, well, I mean, a diagonal field is a special case of a non-diagonal field. So a VP of some with a momentum P is just V0 to beta P. Well, the first cat's index is 0. So now, now I want to make a similar identification of a weight changing puncture with a special type of loop ending puncture with 0 loops ending there. So this is not a very rigorous argument, but the idea is that this puncture should come with some weight depending, well, on the angles of loops around loops that goes around it. I mean, what's the total angle, let's say? I would say it's 2 pi, or it's minus 2 pi, if the loop has the opposite orientation. Right? But I cannot have loops with angle 4 pi, for example, because these loops are supposed to be non-self-intersecting. So therefore, I expect this loop to come with some weight, which would be, according to this formula, basically, e to the I pi s plus e to the minus I pi s. Here I'm taking a total angle of 2 pi, and this is just 2 cos pi s. And now, what is this S? Well, this S is 2 beta p. So W is 2 cos 2 phi beta p. So that gives me the weight of the weight changing pressure as a function of the momentum in the CFT, or conversely, the momentum when I know the weight. And finally, I still have to find the weight of contractible loops, but that's now very easy because a contractible loop, if you want, can be viewed as a loop with inside a trivial field, namely the identity field P11 degenerate. So I just have to take this formula, but with the momentum of the trivial field P11. So let me remind you the formula for PRS. So that was 1/2 beta R minus beta minus 1S. And therefore, N is, well, if you do a calculation, minus 2 cos pi beta squared. And if you remember this N, well, this N was also the N of the ON or the UN model. I mean, that I'm not doing the argument, but the argument comes from mapping these models with some n-dimensional vectors to a model of loops.
So beta square is G in terms of. Okay.
Right, so beta squared is related to the central charge by C equals 13 minus 6 beta squared minus 6 beta minus 2. Okay, so we know the mappings of the basic parameters of the models. And now let's map the correlation functions. So in the CFT, we have product P R I S I. And this should correspond to some statistical loop statistical sum I wrote before. Now, this quantity so far is not completely well defined in our CFT because I mean we are in the bootstrap approach. So we could say, okay, let's define this as a solution of crossing symmetry. But then to even write the crossing symmetry equations, I have to tell you which fields propagate in any channel. So let me make assumptions about that. So, for example, let's consider a 4-point function in the S channel. So, to begin with, I'm assuming that all possible non-diagonal fields propagate, provided they obey the conservation of R modular integers. So the S channel spectrum will be made, first of all, of all VRS with R such that R is equivalent to R1 plus R2 modulo integers. And then I have to say which diagonal fields are allowed to propagate. And here I will take this information from the loop model because I want to reproduce the loop model statistical sums. So in the loop model, the question, I mean, is whether we will have S loops. So if I have some combinatorial map, this map here allows for the existence of an S loop. So a loop which separates the vertices 1 and 2 from the vertices 3 and 4. And so which comes with its own weight, WS. On the other hand, some other maps don't allow S loops, but if this conservation of R is obeyed, then some maps will allow S loops. So I have access to a parameter WS, and the conjecture is that I'm allowing all the diagonal field VP such that, well, the corresponding loop weight W of P is indeed WS. Well, of course, there are infinitely many such fields because here W is a trigonometric function of P. So, to be more precise, I mean, this is the same as, if you want, BS plus K beta minus 1 for K an arbitrary integer. Okay, so we'll take this as the S-channel spectrum, and similarly, you can specify the spectrum in any channel in any n-point function. Well, basically, the non-diagonal sector is easy, so it's the same, and the diagonal sector just depends on whether you have these loops. So specifying this spectrum defines your crossing symmetry equations for this n-point function. And so it defines, I mean, these are linear equations, and therefore we have a space of solutions. We don't know if we have a unique solution. We have a space of solutions. So let's call this space, let's give it a name, probably C. Yeah. Well, it's supposed to be a curly Z, which is not the same as the Z, which was just one particular. The space of solutions of crossing symmetry, given this n-point function and given all the weights of these possible loops. And now, what should it correspond to the loop model? Well, in the loop model, we are supposed to know some of these solutions. In fact, for any combinatorial map M, we define a statistical sum which depends on M. Or more precisely, this is a statistical sum, but we want to take its critical limit. And we think this is a correlation function in the CFT. So we think this belongs to this big space of correlation functions. Now the conjecture is that these statistical sums form a basis of this space. So they are linearly independent as functions of all the parameters, and they span this C. So V is the span of this space Zn.
Your M is for a map here?
Yeah, M means the combinatorial map. So I think I need to give an example.
Sorry, why a priori you ask that the span is equal Z and not just a subset of subspace?
Well, this is the result of a numerical experiments by
Okay. You already.
symmetry. I mean, it's a course. I'm not presenting things in the order they came in the actual research, right?
Okay, okay.
So, in general, a conjecture like that is the result of a lot of testing and trying.
Okay, that is life.
But I want to give an example which shows this conjecture at work. So I gave actually an example last time of a number of combinatorial maps. So if you're considering, for example, a correlation function of the type V, 3 half from S1, V1 half S2, V1 S3, and some diagonal field, VP4. So this should correspond to vertices of a trivalent vertex, one valent vertex, bivalent vertex, and some function. And then what are the possible maps? Well, I can draw them. There were 4 maps, in fact. So there's this one, but there is also this one. What else? There is this one, probably. Up. Yes. And finally, this one. So irrespective of this second cat indices, which don't really play a role in this combinatorics, I mean, we have 4 maps. And this leads to, according to our conjecture, we believe that the space of solutions of crossing symmetry is 4-dimensional. In this case, for this particular 4-point function. To solve these crossing symmetry equations, we also need to know the WS, because here we can have a S loop coming with a weight WS. I mean, that's the only one of these maps where we have this dependence on WS. But it would be even better if we knew which combinatorial map corresponds to which solution of crossing symmetry. Which for the moment we don't really know, but we have another conjecture which restricts a lot the possibilities. So the idea is now to define the signature of a combinatorial map. So for example, I want to know what propagates in the S channel, and the idea is to just draw one of these S loops, even if it crosses some of the lines of the map. And then I count how many lines I intersect. And the signature is half this number. So sigma S in the S channel is 1/2 the number of loops, of open loops, let's say, that cross an S loop. And I can define the signatures in the other channels, sigma t, sigma u. So eventually I can compute sigma s, sigma t, sigma u, the 3/2 integrals which are the signature of my map. So I can do this for these maps. For example, for this map here, the S channel signature is 1, T channel is 3/2, and the U channel would be 1/2. For this map, I will have 2 in the S channel, 1/2 in the T channel, and 3/2 in the U channel. Here, it's 1 in the S channel, 3/2 in the T channel, and in the U channel, 3/2 as well. And here, I have 0 in the S channel. I have 5/2 in the other channel. Okay, any questions on this small exercise? So, now we already see that if we want some diagonal field to propagate in some channel, we need the signature to be 0, because that's what corresponds to having a S loop which doesn't cross any edge. But this observation is generalized, in fact, to the idea that if R is less than the signature in some channel, then the corresponding 4-point structure constants, DRS, are 0. So let me remind you, what are these 4-point structure constants? Why this is important. So the crossing symmetry equations, they look like well, sum of D x, well, let's say ds k with some block G delta k equals the same in the other channels, in particular dkt jt delta k equals for the U channel. But now I'm adding extra equations here from this constraint. So each map comes with a number of extra equations. And now it can happen that with these extra equations, the solution becomes unique. And if it does, then I know which correlation function is supposed to correspond to which map. But it doesn't work all the time. It works only for some maps in some cases. So this is not a very this is not a complete answer. Okay, any questions about this? Well, you seem a bit puzzled. No? Well then, okay. Then.
I was just wondering, is there a relation between the signature and the sum of Ri, for instance? The sum of signatures is the...
Well, the sum of signature is not always the same. So, but I think there are inequalities. Okay. I mean, the signature is something we made up for conformal field theory. I'm not sure it's a standard concept in combinatorics of maps. So,
these are not really maps.
no, these are combinatorial maps.
The graphs, really, on the lattice.
Well, maps are a type of graphs.
Maps. Bit by extension. It's not really the maps we have in Gutenberg.
Well, these maps at least are the same as the maps of our colleagues Emmanuel Guiter and Jérémy Boutier. I mean, I use their papers actually to count the number of maps. I mean, this number of maps, 4 maps, I mean, is the result of a formula in their paper. Right? I mean, they have formulas which tell you, as a function of the parameters R1, R2, R3, R4, how many maps exist. These formulas work in our case. The formula is basically, for a 4-point map, is basically sum of Ri squared, plus maybe some constant, depending on Ri modulo 2. Modulo 1, sorry. But that's for 4-point maps. So for the 5-point maps, it would become quartic in Ri, etc. Okay, so now for some maps we have a unique solution of the bootstrap, and then we can compute, I mean, numerically the structure constants, and then we can try to find analytic formulas, an exact formula for these structure constants. So that's what we'll do, but not immediately, because I still have one thing to discuss about these loop models and what happened in the critical limit, because I was very, very sketchy here, and I want to give you slightly more detail, and also to discuss for which values of the central charge you can take the critical limit. I mean, for which values of C, or which values of the parameters n of the statistical models. Yeah, maybe I want to keep these equations. Okay, so you can define a lot of different statistical models which will end up being loop models in the critical limit. I mean, you have a lot of choice. If you are thinking of lattice models, you can decide which lattice you want to have. It could be a square lattice, or maybe a hexagonal lattice, or even some other lattice. And then once you have a lattice, you have to decide how you draw the loops on the lattice. What are the rules? For example, do you want each side of the lattice to be visited by a loop or not? Or do you allow empty sides? Do you want each edge to be visited by a loop? I mean, the basic rule for us is that the loops don't cross, but apart from that, you have still a lot of choice. And when you, after making these choices, you will allow a number of vertices. And each of these type of vertices could come with a statistical weight. So this gives you parameters for your model, so which I will call generally couplings. Well, for example, in a square lattice, a vertex like that, and a vertex like that, they may have different couplings. Okay, so the basic idea is that when you take the critical limit, a lot of these choices don't matter, and you end up with the same conformal field theory. And that's the idea of universality. But we want to be slightly more precise and see from the conformal field theory what we can say on these critical limits. And these critical limits will be influenced by the existence of relevant fields in the conformal field theory. So what I call now relevant is a primary field whose total conformal dimension, well, in real part, is less than 2, 2 being the space-time dimension. And then we look at marginal fields. If the real part is 2, and you have irrelevant fields where it is more than 2. And the idea is that irrelevant fields don't matter in the critical limits, while relevant fields matter a lot. Well, more precisely, the idea is that relevant fields should correspond in your statistical model to couplings. And for the critical limit to exist, you have to set these couplings to certain critical values. Fine-tune these couplings if you want. So if, let's say, if you define some loop model here, and then you forget some coupling. In other words, you end up with having a relevant field which doesn't correspond to any coupling, then typically you won't have a critical limit. Because forgetting this coupling means essentially setting it to 0, and the critical value could be non-zero. Unless some symmetry intervenes and protects, if you want, the critical limit from this particular relevant field. Okay, so that's the general idea. And now we want to see how this works in our loop models. So what are the relevant fields? Well, for simplicity, I'm going to focus on the degenerate field, P1S. Well, of course, you have a lot of other fields in the spectrum, in particular the non-diagonal fields. But, okay, at least these ones are particularly important because in the models, in the specific loop models we can consider, like ON, UN, post model, they will transform in the trivial representation for these global symmetries. And therefore, well, there is no symmetry that would save you if you forgot to have corresponding couples. So, or said in other words, no symmetry would prevent these fields from derailing the renormalization group flow from taking the critical limit.
So if you do that, you have only loops.
What do you
If
mean?
you restrict yourself to V1, V1S, you have only loops in your drawings.
No.
Because these are two layered vertices.
No, I want to restrict in the sense that I only want to study whether these fields are relevant or not. I'm not saying that the other fields don't exist. I'm just saying that I'm not studying in detail whether the other fields are relevant. So, what is the dimension of these fields? So these fields are diagonal, so they have the same left and right dimensions. So we have to consider whether the dimension of such a field is less than 1. So let's compute delta RS minus 1. And then there is a simple way to compute it, which is PRS squared minus P1 minus 1 squared. Because 1 is also the dimension, if you want, of the field of, in this field, 1 minus 1. So, to compute this, well, we can do this. PR plus 1, S minus 1, PR minus 1, S plus 1. And now, taking the first index to be 1. So this is 0. So here I'll get a minus s plus 1 over 2 beta inverse times beta over 2 r plus 1 minus s minus 1 over 2 beta. Which is s plus 1 over 2, and then, well, let's say s plus 1 over 4, s minus 1 over beta squared. Ah, but no, r is 1, so I use it in here as well. So r equals 1. So this is 2, in fact. Okay, so minus 2, right? So the condition that the real part of this, that the field is relevant, if the real part of this is less than 0, is equivalent to the real part of beta minus 2 less than 2 over s minus 1. And let's draw this in the beta. Well, we don't consider s equals 1. I mean, this is the identity field, and it's a trivial field, which does not really matter for the critical limit. So, but you're right, I should exclude explicitly s equals 1. No, let me start more on the left. I mean, so that's the beta squared complex plane with 0 here. So why am I drawing only the right of the plane? Because the CFT doesn't exist on the left. I mean, this was the condition that the real part of beta squared had to be positive. Otherwise, the OPs don't converge due to the presence of all these non-diagonal fields. Okay, then I'm drawing only the upper half plane, basically because the lower half plane is the same by reflection. Okay, so what are, I mean, these lines, I would call them marginality lines. So if re beta squared equals 2 over s minus 1, this is the line where some of these fields are marginal. So, do you recognize the shape of these lines from this equation? Well, this line is the image of a straight line and an inversion, right? I mean, here I'm inverting beta. If it was not beta inverse but beta squared, it would be just a straight line. And the image of a straight line and an inversion is a circle. So in fact, this is a circle, and all this circle goes through the origin. So the first circle for s equals 2 is this one. It goes through 1/2. So that's s equals 2. I'm drawing a dashed line because this s equals 2 degenerate field is not present in the ON model. So I will want to discuss specifically the ON model, but it doesn't have this particular field. On the other hand, the ON model has the field V13. So for s equals 3, I get another circle which goes through the point 1. So that's s equals 3. And then it goes on like that. So the next circle here for s equals 4, and the circle, the marginality line of V15 is this one, and etc. So now what is the physical interpretation? So let me start inside this circle. So that's a region where my the field V13 is irrelevant, in fact. It will be relevant outside this circle, but it's irrelevant inside. And in fact, inside this circle, there are no relevant fields at all. And correspondingly, we expect that the loop model has a critical limit without tuning any coupling. And that's what happens. And this is the so-called dense phase of the ON model. So, in this dense phase, well, provided the coupling is large enough, the model has a coupling, but if the coupling is large enough, you don't have to tune it. You have a whole range of values such that the critical limit exists. Okay, so here, traditionally, this dense phase is taken to be this half line here, beta squared between 0 and 1, but now I'm claiming we can extend it to the complex plane to this circle. On the other hand, if you reach the boundary of the circle, then something happens. Your dense phase, your dense model is no longer critical. Now, similarly, for beta squared between 1 and 2, usually we define the dilute ON model. So the dilute model has also one coupling. This coupling corresponds to the marginal, to the relevant field V13. And for the critical limit, you have to send this coupling to fine-tune it to a critical value Kc. And now, again, if we want to continue beta to complex values, well, the conjecture is that so long you're inside this circle, everything is fine. But then at some point, you may reach your dense phase and your coupling stops being relevant.
What happens with the S equals 0? The operators with S equals 0.
No, we consider here only degenerate fields. So degenerate fields don't have S equals 0. So you have a non-diagonal field with indices 1 and 0. That's the one you were talking about?
Yes.
So the one.
Any point along the
this one, I don't think it's, I think it's probably irrelevant in this region, but it should become relevant somewhere in this whole complex plane.
They're always relevant. It's always relevant. Gives you the order of dimension of the loop. So this one has that gives you a dimension which is positive. So it's relevant.
It's always, you mean less than 1, the delta 1, 0? Or maybe we should delta 1, 0, 1, 0 squared. Well, in fact, this is again
your equation.
Yeah, it's again the equation.
S equals 0, just
yeah, this equation here.
No, the one.
No, but I think
the next one.
Yeah. Okay.
It's negative.
Oh no, you're right. So it's always relevant. So I think that this is not a problem for the ON model, because in the ON model, this thing belongs to a non-trivial representation, which is a symmetric 2/10 of ON. So by ON symmetry, basically, it doesn't matter for the critical limit. Okay. But if you broke ON symmetry, probably it would become a problem. Or you would have a corresponding coupling and you would have to fine-tune it. Okay. And next, what happens if you go outside this circle? So when this circle is the marginality line for V15.
When you take this other one, the simplest one with just a weight for the loops and a weight for the number of 5. That
Right, that's the case here. No,
no,
you think it's the one for V10? maybe we have to check that.
Because you have the speed here.
No, it doesn't have any speed. It's a diagonal field with the same left and right dimensions.
Okay,
Yeah, we can discover it. Okay, yeah, so we have this marginality line for V15, and if we go outside this big circle, V15 becomes relevant. So if you want to have a critical limit, you have to add a coupling in the lattice model corresponding to V15 and to fine-tune this coupling. So this phase, so we have the dilute phase here, the dense phase there, and outside we have the so-called multi-critical phases. Multi-critical, because you have to tune several couplings to reach the critical limit. And okay, now maybe we are not so interested in this parameter beta squared. Maybe we are more interested in the parameter n, which was the original parameter of our model. So let's map this to the complex n plane using the relation n equals -2 plus pi beta squared. And this relation is not one-to-one. So the whole complex n plane, in fact, corresponds to one of these vertical strips. Actually, it's a reason why the same CFT can describe so many different phases of many different models. Because each statistical model typically will exist on a portion of the complex n plane. But this portion is itself a portion of a strip. But the strip, I mean, the CFT has a much larger range of parameters. So, these points, 0 and 1, they correspond to -2 and 2. So, in particular, this red segment here, this red segment here is the red segment here. And then we have this forbidden region. So the forbidden region, you don't have it in this n plane because this boundary here is just this line. And then you have the other boundary of our n plane. So this vertical line, which is this one. Now this circle here gets mapped to some region which looks like this. Except that I drew it too big, so I won't have space for much else. So that's the typical region of the dense ON model. And then the next line here, for the marginality line of V15, well, it looks like this. Well, I'm running out of my blackboard, but it's something like that. So, if I'm starting from the dense ON model, then I'm going out of this region. I'm reaching the dilute ON model, but I'm a bit far from the original region when it was defined. To go there, I have to cross this line, so I have to cross this kind of branch cut, and then I reach another n plane, and in this other n plane, I can analytically continue until I reach this segment. Well, that's the idea. Now, how to do this in terms of a loop model is probably a challenge. But that's the picture from the CFT. So now in the loop model, I mean, how do we interpret these lines? I mean, apart from just vaguely saying that the model stops being critical, I mean, what do you see actually if you do a loop model on a lattice? So there were recent works on that, and the idea is that in the loop model you will see zeros of the partition function. And these zeros will tend to condense on these marginality lines. For example, for some finite lattice, you might have these zeros along this shape here. And when the lattice size becomes infinite, you expect that they form this marginality line. Well, actually, you have other zeros of the partition function, which are not always on the marginality line, You also have zeros when the ground state changes. And ground state means the field with the lowest dimension. And the field with the lowest dimension, it can be a number of fields. In the ON model, it could be V11, just the identity field, but well, it could be V10. It could be V20, I think. In the Potch model, it could be VP01 the diagonal field. So if you have the ground state changes, you see some non-analyticity in the free energy, and you see that as well in your partial function. In addition to the marginality that.
What do you do when you need to negative x? You know, when you are below 0, but you know your partial function change signs. I mean, your terms change sign.
Yeah. Well, even complex, they don't necessarily have a sign if you take them complex. I mean, negative is a bit tricky because, well, at least this range is really forbidden now. We don't even have a CFT. I mean, you mean negative between -2 and 0. Yeah, I'm not sure. I mean, I'm just using here the 14-castelling reformulation of the model, so which is a sum of n to some power and some integer power. Your lattice model. So n can be any number, any complex number. However, yeah, this thing is no longer positive or anything. This term is not positive for negative. Well, it depends. In the UN or Potts model, typically you would take these numbers to be themselves even, so eventually it's still positive. But in the ON model, I don't think so. Okay. So I think that's all I want to say about these lattice models, and that's a good time for the break. And after the break, I propose to discuss how we determine analytically the structure constants of the CFT.
Do we have some questions, or do you need a break? No break. No break.
We want to solve the CFT, which means to compute exactly all correlation functions in principle. Well, in practice, it means computing the structure constants. Now, we are in a good position to do that because with this story about combinatorial maps, we can build specific, we can compute specific 4-point functions and get numerical results on the 4-point structure constants. So, if these numerical results, I mean, if we have no idea of the exact form, we can't do anything with numerical results. However, we have so-called reference structure constants, which we found when solving the shift equation. So the shift equations are consequences of the existence of degenerate fields, BP12 in particular, and they told us how structure constants behave when the P goes P plus beta inverse. And I propose that there were very simple solutions of these shift equations called reference structure constant. So here I'm rewriting the 3-point reference structure constant here, which is a product of 8 double gamma functions, or rather one of the double gamma function, gamma beta, with here an absolute value for the first Katz index, R1, R2, R3, and also a term with the second Katz index. But then there's a formula I didn't write, which is the 2-point reference structure constant, but the idea is just the same. You solve the shift equation for the 2-point function, and you write the solution which you find nice. And this BP is just the solution for the diagonal 2-point structure constant. The 2-point function, if you want, of Liouville theory with C less than 1. The 3-point case includes also diagonal fields. If you want, you can say R equals 0 and you get the diagonal case. So by this identification, B0S is So the non-diagonal field V0s is the diagonal field 1/2 beta minus 1x. So these solutions are not unique because we have only one shift equation for the shift by beta inverse. We don't know, we don't have the extra degenerate field B21, which will be needed to fix the shifts by beta. So these solutions leave a lot of freedom. And basically, the freedom we have, if we look at the dependence on P, the momentum of the diagonal field, so the freedom we have is any function of W, which is 2 cos 2 pi beta P. Because W is a periodic function of P. So now the question will be which types of function of W will we need to add to get the exact results. So let's focus a bit more detail on the 4-point functions we might want to compute. So let's consider a case when we have some diagonal field propagating the S channel. So that's the case we saw before. So let's have a Z of P, a 4-point function, which is a function of the S channel momentum P. Now it's called P, not PS. So it's a combination of the diagonal sector, which is just D P plus K beta inverse, and then F P plus K beta inverse squared. So D is some structure constant, which we don't know for the moment, which we would like to determine. And F is the conformal block, which in principle we know. So more precisely, Fp is a S channel Virasoro block. So the contribution of a Verma module with a primary field of dimension P, and then you sum over all its descendants, and you get this Fp. And then to get the full result, since we have the left and right Virasoro algebra, we have to take this modulus squared, which is not really a modulus squared, but which is multiplying the left movers by the right movers. Okay, so that's the diagonal sector contribution to a 4-point function. And the non-diagonal sector, well, it's always the sum over the spectrum of the non-diagonal fields. So R is a strictly positive integer, S is a fractional number, and we have a structure constant DRS, which now is a function of P, right? Because, well, everything is a function of P now. Well, except of course the block. So here we have a block GRS, which is a universal object, which cannot depend on P. And I don't write it as a modulus squared, but for a good reason. Well, in fact, GRS is a modulus squared, meaning it's left-right factorized in many cases. So, unless R and S are both integers, non-zero integers, then GRS is just F PRS F bar P R minus S. I mean, why is that? Because I mean, GRS is the contribution of basically the non-diagonal field VRS and its descendants. So this non-diagonal field has left momentum PRS and right momentum PR minus S. But this formula cannot be true if R and S are both integers, because we know that the block here has a pole. It has a simple pole for at PRS if R and S are positive integers. So this pole came from, well, it came from the pole in the OPE, which itself was due to the fact that you have a null vector in this Verma module if R and S are integers. Okay, so this formula is wrong in this case, and in fact we'll find the correct formula. But for the moment, we just write some GRS, which we don't fully know, but which is supposed to account for the contributions of this non-diagonal fit. Okay, any questions? Okay, so now, what do we know already on this subject? So we know that Z of P is invariant on the shift by beta inverse. So that's a consequence of the existence of a degenerate field. So this implies, I mean, I could have written Z as a function, in fact, of W, of this weight, but it's more convenient to write it as a function of P. But still, this invariance here implies in particular that if RS of P is also invariant. Okay. So now let me make a first non-trivial assumption. So I will assume that I know this structure constant dp plus k beta inverse. All these dp basically. Structure constants for diagonal fields. So I will assume they are given by the reference structure constants, which were these particularly nice solutions of shift equations. So I'm assuming dp is just a combination of the reference structure constants which you would expect. So Cref, P, R2, S2, R3, S3, Cref, P, no, it was, sorry, R1, S1, R2, S2. Here I'm considering, if you want, this channel diagram. 1, 2, 3, 4, and here I have P in this channel. So Cp, R3, S3, R4, S4, divided by Dp. So I'm assuming this. I mean, if you take an individual function z of p, this is not a big assumption because, I mean, z of p is defined by crossing symmetry equations which are linear. So I have the freedom to normalize, and I can decide that I normalize one of these diagonal fields here by choosing this value for its structure constant. And then all the other diagonal fields, well, they have to have the same formula because this is a solution of the shift equations, and all these values of p plus k beta inverse are related by these shifts. So this solution of shift equation must also work for all diagonal shifts. Okay, the next assumption is much stronger now. I want to assume that z of p is holomorphic in P. Okay, do you think that's a reasonable assumption? Well, think a bit of the loop model. So in the loop model, originally, the statistical model, P appears through this weight, W, and the loop model, in the loop model, this Z has to be some sum over a lot of loop configurations of some W to some power. So for any finite lattice size, in fact, Z is a polynomial in W. So that's why it sounds reasonable that in the critical limit, Z could be holomorphic in W and therefore also in P. Okay, I just claim it's plausible. I did not prove anything.
That's sketchy, right? Because we are very used to getting non-analyticity when we take critical limits, when we take continuum limits.
Right. So in fact, I could try to do this argument for n, and in fact, it doesn't work because eventually the result is not analytic, it is not holomorphic in n. So yeah, something is missing in this argument. I agree, but okay. The point is, well, I don't know. I mean, these small contractible loops, they are really everywhere, but these loops are larger. They cannot get very small, so maybe this protects, if you want, the holomorphicity. Well, here this is an S loop, so basically it's a loop which has to separate the points 1 and 2 from the points 3 and 4. So this loop, yeah, has a minimum size. And you can't have that many loops of this type, whereas the small loops there, contractible, and you can do a lot of weird things with them. Okay, so but anyway, I'm in an arithmetic approach, so I'm allowed to make assumptions until the house crashes down on me, so let's see if it crashes down.
Sorry, just a stupid question. According to your notations, absolute value square is defined nearly everywhere from the f times f bar.
Yeah. So
and what about p? When you see dependence of p, you keep the homomorphic dependence of p. You keep the same p in both of them.
Yeah. Well, in this case, it's the same p because it's a diagonal field.
Okay.
If I had a non-diagonal field, I would take p bar, the right momentum, but here there's no right momentum. I mean, it is the same as the left.
Okay.
So I could have used this notation here if you want, but I prefer to spell it out explicitly. Because here the right momentum is different from the left. Okay, so I could say this argument is at least plausible. I mean, this assumption is at least plausible from the loop model. Now, from the CFT itself, it's not so plausible at first sight because these blocks, well, they have poles. And the structure constants, in fact, also have poles. So we have plenty of poles in this kind of sums, and these poles have to all cancel if I want the result to be holomorphic. So we have to study these poles in slightly more detail. So let's start with blocks themselves. So as I reminded you, this block has a simple pole when P is PRS with R and S positive integers. And let me write it more precisely. Fp near P is PRS. So here R and S are strictly positive integers. So Fp is just some residue Rs over P minus PRS times a residue FPR minus S. Well, I'll tell you why this is the residue, plus some finite term which I call F regularized, PRS, well, plus negligible contributions of order P minus PRS, let's say. Okay. So why is the residue FPR minus S? Then you have to remember this formula is just an expression at the level of conformal blocks of a simple algebraic relation, which is when you have the primary field of dimension delta Rs, it has a null vector somewhere. By definition, the null vector is also a primary field, and it's a primary field of dimension delta R minus S at the level R times S. The level is the difference of these two dimensions. So when you consider the Verma module, here you have a big Verma module, you have a sub-Verma module generated by this null vector. And due to this null vector, when you compute the block, you get infinities. And the infinities come from this null vector plus all its descendants, which is the same as saying that the residue is the contribution of the null vector and its descendants. In other words, it is the conformal block. And then we have residue here, some number RRS, which is known, which I'm not writing, but which can be computed. In fact, our argument will give us a way to compute. Okay, so knowing that, I know that my Z of P seems to have poles, second order poles in P, right? So the first priority is to cancel these second order poles. So where do they come from? I mean, so first, therefore, we have a second order pole at P is the PRS. And the residue of this pole is proportional to F P R minus S squared. The second order residue. So to cancel this, I need a contribution which is also proportional to this block. And this contribution will come in this sum from the term K equals S. Because if I take K equals S near PRS, I get PRS plus S beta minus 1, which is PR minus S. And therefore, I get a term with the block FPR minus S squared. So to cancel the pole, the second order pole, I need this number now, D, to have itself a second order pole. And in fact, that is what happens. So if you look at BP, BP has a second order 0 now. So let me remind you that the D, the structure constant, has a denominator BP. BP has a second order 0. And so there is a chance they cancel. So more precisely, the equation which you need for cancellation is RRS, R bar RS, D PRS, which is finite, plus the limit equals to PR minus S of P minus PR minus S squared dP is 0. So here I'm just computing the coefficient of this block here. Coefficient which comes from two terms. And in fact, from this equation, I could compute up to a sign these residues of conformal blocks. Because I mean, this dP is something which we know it. Yeah. So let's say we are happy about this cancellation, but we said this dP has to be holomorphic, not just that the poles have to be order 1. So we have to cancel order 1 poles as well. So let's again look at P equals PRS and see if we can cancel the residue now. I mean the first order residue of P. And well, not just D of P, sorry, I mean I want to cancel the residue of Z of P, the first order residue. So in principle, now I can compute the residue from the diagonal terms, and the point is that this residue is non-zero. So to cancel this residue from the diagonal terms, I need to have a contribution from the non-diagonal terms. And in fact, that's what happens. So more precisely, well, this leads to an equation that the residue of P equals PRS of DRS of P, the coefficient of the non-diagonal term, should be R bar RS DPRS. Because as I'm going to argue now, I mean this block GRS is proportional to the first order residue of Z of P. So GRS basically is this thing, F PRS FR P minus PR minus S. But if you look at this FP, at this FP squared, when P comes near PRS, if you look at first order poles now, so let's say the left movers, well, for the left movers, you just don't take the pole, you take the regular term, so you get an FPRS. And then for the right movers, you take the residue at the pole, so you have a first order pole, PR minus S. And this looks a lot like what you expect from GRS. So therefore, these terms have a chance to cancel. And in fact, we want the structure constants to make them cancel. But for the cancellation to really work, I need this block GRS to be just what I need, and what comes from the diagonal terms. So that's what I want to do next, to determine this block GRS. But I think I can be maybe sketchy here and leaving the details in the notes. So it's really a straightforward calculation. We just compute this residue here from this diagonal term, taking into account the behavior of the blocks and also the behavior of the structure constants. And the result is that you want GRF to be of the following form. So F regularized PRS minus RRS prime PR minus S times F bar PR minus S plus RRS over R bar RS F PR minus S F bar regularized PRS minus RRS F bar prime PR minus S. And now I need some more space, so let's erase this German module. RRS D prime PRS over D PRS plus, no, minus limit equals to PRS 2 over P minus PRS plus D prime over P times F PR minus S. Yeah, sorry for the somewhat heavy expression, but this is a straightforward calculation, although tedious. So what do we notice in this block? I mean, the derivatives are with respect to the momentums. What's the feature of these blocks? Well, as a function of the momentum, the block FP starts with z to the p squared, basically. So that's the free factor, which is dictated, in fact, by conformal symmetry. So if you start taking derivatives, as we do in this block, I mean, we are taking derivatives of blocks, we are also taking these regularized blocks here, and if you compute it, it also amounts to taking the derivative of this free factor. So if you take derivative with respect to p, you get logs of z. So basically, these blocks are logarithmic conformal blocks. Yeah, which you can derive by this argument. Okay, so so fine. So it's plausible, at least, that our and holomorphicity assumption holds. We can hold, and what we get as a bonus, if you want, is the determination of the residue of DRS. And now that we know this residue, well, at least we know something non-trivial about this non-diagonal structure constant. I mean, the diagonal structure constants, we just assumed we know them, but this one we don't know anything so far. But now we got some exact constraint, this equation. And so we have to make the most of it. We can, so let's write this DRS of P now. But again, we want to compare it with reference structure constants. So let's define a reference 4-point structure invariant.
But what about higher regular terms P minus PRS? I mean, you could have a GRS corrected by these terms or not?
Well, I'm just here deriving all the consequences of the holomorphicity assumption. So this assumption says nothing on the higher terms.
So you mean GRS could contain some corrections in terms plus order, higher order?
No, GRS is just this. I mean, it's an exact formula.
Okay, but there in your expressions for ZP, you could not have other terms that come from this sum of RS, no?
Well, in fact, no. This is enough for making all the poles cancel.
No, that I understand.
So you can't get
You ask some minimality, something like that. You ask the GRS is defined to be such that the pole cancels.
right.
But then you could add any term to P minus PRS, for example, to G, and the poles will still cancel. So you have several prescriptions to.
Yeah, but GRS is not a function of P. The coefficient is a function of P, but GRS is not. Okay, so let's define a non-diagonal 4-point reference structure constant just by combining the 3 points. So we get some CRS 2 reference CRS 34 over DRS reference. And then we write DRS as the reference structure constant times something. And the something is some small DRS plus the pointer, because I know we have a priori non-zero residue here at this pole. So the pointer, well, is some residue, which we know, divided by what? By W minus W of PRS. Because now I start to remember that things are not a function of P, but they are a function of W, in fact. So it should be. So then the idea is, let's write this more explicitly. Let's compute actually this residue, and also let's write such a formula, not just when I have a pole, but also more generally for any 4-point structure constant. Because to have a pole, we need our combinatorial map to allow for S loops, and moreover, we need the S index to be zero, to be a non-zero integer. So this is a really special case. So that would be, if you want, for sigma equals 0, sigma S the S channel signature, and also if S the second cat index integer. But no, in general, let's write DRS equals dref times some small d plus, well, if there is a pole, we want it. So if there is a pole, which means delta is 0, if sigma, the signature is 0, and if S is integer, then we want this pole, and let me write its residue explicitly. So the residue is -1 to the R plus 1s times some rho Rs 1, 2, rho Rs 3, 4. And rho now, I mean, you get rho just by explicitly computing this, combining the formulas we have written so far. And you find, I mean, okay, a priori it's a big combination of double gamma functions, but as you know, double gamma functions, they're the shift equations. So you reduce everything to gamma functions, and then the gamma functions, then you combine them into trigonometric functions. So at the end, it happens to be trigonometric, which is also why we chose this reference prefactor. So if you want, we put everything that's non-trigonometric in here, and we are left with a trigonometric residue. And this residue is, okay, there is a sign prefactor which I'm omitting, and then there's a product. J equals, so J runs by steps of 1, R minus 1 minus R1 plus or minus R2 over 2 until R minus 1 minus R1 plus or minus R2 over 2. Okay, so J equals, and there is a minus before all this. And then what I have a 2 cos phi J beta squared plus S minus S1 plus or minus S2 over 2. Okay, so that's the residue. So now, the observation is that this residue is itself polynomial. Polynomial in N equals minus 2 cos phi beta squared. It's also a polynomial in, if you want, W1 and W2. If R1 is 0 or R2 is 0. So, okay, rho Rs is a polynomial. So what is the next natural conjecture? Well, anyone has an idea? Or a question to better understand what comes before? I mean, you should not be afraid to make conjectures. I mean, in this business, you have to make conjectures all the time. Otherwise, you don't make much progress. So,
The D over D ref is a polynomial.
yeah, so more specifically, I gave a name to that. It was called small d now. So indeed, the conjecture is that Pi is a polynomial. So polynomial in what exactly? Well, first of all, in this W here, so in the channel weight, the S channel weight, if it is present, also polynomial in N, the contractible loop weight, and if I have some diagonal fields in the business, let's say field number 1 could be diagonal if R1 is 0, it also has to be polynomial in W1, or more generally Wi, for I equals 1 to 4. And this conjecture allows us to interpret our numerical results for DRS. Because if we have some number, some numerical result, we divide it by the dref, we subtract the pointer, if applicable, and then we try to match it with some polynomial. So if this polynomial was of high degree, like 1000, we couldn't do much. But of course, we start with low degree polynomials, and with some luck, we do find a match. So we do find polynomial expressions for this small DRS. So let me give these expressions in some examples. So the first example corresponds to the trivial combinatorial map when we have 4 diagonal fields. If you want, I'm considering a 4-point function, product of VPI. So there is only one combinatorial map corresponding to this 4-point function. right? I mean, I don't have lines, there is nothing I have to choose. So what are the results? So with D10 in the S channel, you find it's plus WU. I mean, I'm giving you the S channel result because in the other channels it's very similar by permutation symmetry. D11 WT minus WU. And then you have slightly more complicated results for D20. So that's L squared minus 4 times WT squared plus WU squared plus 2WS minus 4 minus N minus 2 WT plus WU W1 plus W2 W3 plus W4. Okay, so that's an example of the type of polynomial we find. So this case is particularly interesting because I have continuous variables for my 4 fields. So I can in principle study whether this structure constant factorized into factorized a bit like my reference structure constant. So factorized into 2 vertices. The vertices, let's say 1, 2, and the vertex 1, 2, and the vertex 3, 4. And in this case, I see that this formula is not factorized. In fact, it's a sum of 2 terms. This term is factorized. This one is trivially factorized. Well, in fact, I have an extra term which I didn't write, which is the pole term. So the pole term is also factorized. It's one more term. Except that, in fact, sorry, I forgot one term. But the term I forgot is very similar. It's n plus 2 W3 minus WU, W1 minus W2, W4 minus W3. Sorry, so in fact, if you want to factorize this, you have three terms. For this D20, and if you want to factorize the full structure constant, you need 4 terms. D20. But we don't know what each of these terms corresponds to. I mean, this is just, let's say, experimental data now. Okay. So let me give a couple more examples. So we have the case of V150 4 times, and I'm choosing this combinatorial map. So here I have an S loop with weight WS. So my structure constants can depend on WS. And then, well, in the S channel, you have DRS 0 if the spin is odd. As a result of the symmetry of this map and the exchanging 1 and 2. So the structure constants are D10 S when it also happens to be 0. D20 is n squared minus 4. D21 is minus n squared minus 4. So strangely, these first structure constants don't depend on this WS. So that's let's say non-trivial experimental result. The dependence will start, in fact, when r equals 4. So I'm still waiting for WS now, because D30 is minus 8 n squared n minus 2 squared n plus 2. I'm not writing D31, which is very similar. I will just be writing D40, which is n squared n minus 2 cubed n plus 1 squared n plus 2 times ws n plus 2 squared n minus 1 squared plus 2n fourth minus 6n squared minus 8n plus 16. Okay, so that's an example of this polynomial. And yeah, from this type of example, we guess bounds on the degrees of the various variables. So the degree of n, you see, it increases with r. It increases more or less like r squared. R in the first calculus. Then the degree in ws, it increases linearly in r. And if we know the degrees, it makes it easier to extract exact formulas from numerical results. Okay, the last example I want to show, just in case you believe all these coefficients of these polynomials are always integral or irrational. In fact, it's not the case. It's not the case, and you can see that in a slightly more complicated example. So V3 cap 0, V11, V10, V1 half 0 with a particular combinatorial map. So do we have any diagonal fields in the spectrum? No, there is no channel where we can split the map and draw some non-trivial loop. So let me just write a few S-channel coefficients. So V1 half 0, it happens to be 0. V3 half 0 is n plus 2. D5 half 2/5. Is 4 cos pi over 10 times minus n fourth plus 4n squared minus 2 plus 5 n plus 1 n squared minus 3, when of 5 is the golden ratio. Or if you prefer, 2 cos pi over 5.
What you get?
Well, the idea is that you get trigonometric factors because of this weight. So S appears in the loop model as weight factors e to the I s over 2 times some angle. And eventually this gives you trigonometric factors, but will depend on the second cat indices. So here you have a 2/5, so that's why you get 5 in the denominator. But in this, yeah, that's the general idea. So we have trigonometric numbers, but we have an idea a priori which type of trigonometric numbers we can get, so we have a chance of guessing them. It would be better to have a general formula, but for the moment we don't. And so I think I'll stop here. I mean, it may look like I'm stopping in the middle of the story, but I mean, the course is about solvable CFTs. It's not about solved CFTs, or not only about solved CFTs. So this one, I mean, from this type of results, when we believe it's solvable, we can get a number of exact results on the case-by-case basis, but it doesn't mean we understand the general structure so far, and we are still a bit far from solving it.